Hey everyone, let's get started on a little bit of a gear shift to introduce multi-section matching networks. And to introduce that topic, we need to first get comfortable with this notion called the theory of small reflections. So you notice I have a single transformer, right? So this should look a lot like the familiar quarter wave transformer where I had an input characteristic impedance feeding some line. There was a load here, and then there was this little intermediate piece of transmission line here with a slightly different characteristic impedance. And you could do some fun things where you would, transform, quote unquote, the equivalent input impedance looking down towards the load. So we're going to explore that notion in a more generic sense. And when we say small reflections, what we're going to do is, very gradually increase or decrease or change the characteristic impedance between these sections. Because what we eventually want to do is arrive at something where there's not just one little transformer, but 2, 4, 6, 8 of these little transformers all connected in series. So that's where we're going, where you get these, they're called like multi-section matching networks. All right, so let's just take a look at the basic physics of what is going on here. So first things first, what you want to do is start labeling a few parameters here. So I'm going to imagine a signal coming in and reflecting here. And this is going to account for all the bouncing back and forth. I'm just going to call that gamma. That is the net reflection coefficient seen looking into this entire system. I'm also going to have what you call the partial reflection coefficients here. So you imagine a signal coming in, it meets this boundary, then there will be a transmission, and then there will be a reflection here. So we define this as gamma 1. Where gamma 1 is defined as Z2 minus Z1 divided by Z2 plus Z1, right? So it's the reflection coefficient at this particular junction, independent of all the other stuff happening down the line. So that's why it's called a partial reflection coefficient. And then I'm going to have another one over here, which the book likes to call gamma sub 2, which will of course be, I'll say gamma 2 is equal to the following: Z sub L minus Z2 divided by Z sub L plus Z2. And you also have a transmission coefficient associated with this boundary here. So you imagine some energy is going to cross this boundary, and then when a signal comes down and back again, it sees the same boundary, and there'll be again a sort of a reflection, maybe looking back here. And so I'm going to call this T 2, 1. So it's the transmission into 2 from number 1, and this will be T1, 2, the transmission into 1 from 2. And I did a slight misnomer here. This should be, this is supposed to be gamma 2. This one here was gamma 3, so we'll do that. So gamma 2 is going to be looking into this direction, is going to be Z1 minus Z2 divided by Z1 plus Z2 here. Okay, so you imagine like a bounce diagram. A signal comes in, there's a reflection and a transmission. Then that transmission comes down and it sees the load. So there's a reflection here and then some, say, energy getting deposited in load. And then it comes back, I see this discontinuity again, so there'll be a transmission again and then another reflection, and everything sort of bounces. So the net accumulation of all of that will be this gamma over here, but all of these terms represent sort of the immediate partial transmissions and reflections. So we have 1, 2, 3 by following the convention in the book here. We also need to note that there is some electrical length here, beta L, okay? And we want to be general here. So I'm not going to give it a specific length. It is going to have an electrical length from here to here. And this term is going to keep popping up over and over and over again. So we're going to give it a symbol theta, beta L, which remember is going to be 2 pi over lambda times the length L. So don't, or you can also express this as a function of frequency, okay? So you can think of this maybe as a theta as a function of omega, or as a function of f if you want, or wavelength here, okay? So that's an important idea, is this, it's kind of a frequency dependent term here, that it captures the electrical distance between these 2 points, or from this node to that node, and so on. So quick little note, you'll notice gamma 2 here is just the negative of gamma 1. And I have these two little transmission coefficients here. So T21 is going to be 1 plus gamma 1, because that's the transmission coefficient, which if you fill it out, you get 2z2 divided by z1 plus z2. And then there will be a gamma 1, 2. So that's the opposite guy here, which is 1 plus gamma 2, which is 2z1 over z1 plus z2. So these are all the partial reflection and transmission coefficients, and then they will all eventually add up to give me a total value here. So remember, you got to think about this in terms of a bounce diagram. So this is 0 here, and this is maybe L. And you have some signal coming in with an amplitude of 1. And this is time in this direction here. So let's go ahead and grab a ruler. There we go. So you imagine there's this signal, comes in, it propagates to here. And there will be a phase delay of e to the minus j theta here, representing that beta L. And it has an amplitude associated with this of T21. Okay? And then eventually it hits the load here. So imagine it comes down, and it's going to now bounce back. So 1, 2, 3, 4, like so. So then there's going to be a gamma 3, because it's the reflection here, and another e to the minus j theta. And then it's going to have a little bit of a transmission there, and then another reflection. So we'll just draw it like that. So each one of these lines is going to have some phase propagation of e to the minus j theta as it goes back and forth. And every bounce here is going to have a gamma 3. Every bounce here is going to correspond to a gamma 2. And then this will be a T12. Okay, and then of course it just keeps on bouncing forever. And so the total reflection coefficient will be, after all of this infinitely settles, you'll get some net reflection coefficient coming down the other end. Okay, so let's go ahead and calculate that right over here, okay? So the total reflection coefficient, the way you do this is you just kind of have to, remember we did bounce diagrams several weeks ago. So we said gamma, you have, of course, there's also a gamma 1 here associated with that initial reflection here. So a signal comes in, there's a reflection and a transmission, reflection, transmission, reflection, and then transmission, reflection. So we got to remember that little term. So I'll get a gamma 1 plus, so then there'll be my signal, my transmission, reflection, and transmission, or transmission, reflection, and transmission again. So you write this as T21, T12, gamma 3, e to the minus 2j theta. So that is this little contribution coming out here. And then it does it again. So let's see if we can write that down. So I will get a T12, T21, gamma 3, e to the minus 4j theta, and that guy is now squared. Okay, so that is now this third term coming out here. And so each term, you're just adding all of those products. So each term is going to accumulate now a phase of this e to the minus 2j theta plus 1 gamma 3 here. So for each little back and forth. And then there's all these other terms now are going to just kind of factor out as we go. So this is going to add up forever and ever out to infinity. So if you write this in its generalist form, you get something like this. Gamma is equal to gamma 1. Sorry, I can't quite see my notes here. So gamma 1 plus, and you factor out a few terms. You get T12, T21, gamma 3, e to the minus 2j theta. And then you get your infinite series out here. This summation from n equals 0 out to infinity. And you get a gamma 2 to the n. Oh, did I miss a gamma 2 here? Oh, sorry. Yes, I missed. There's supposed to be a gamma 2 there. Okay. Because that represents this reflection here. So I'm going to accumulate a gamma 2 with each little bounce. And then there's a gamma 3 to the n. So we factored it out, one of them over here. And then there'll be an e to the minus 2j theta. So that is the general expression for my reflection coefficient looking into any arbitrary single layer transformer here, right? So I have one transformer, there's some arbitrary mismatch here with an arbitrary load and arbitrary distance. After everything adds up, you can express the net reflection coefficient in terms of these partial coefficients here. And this guy in particular is very special because this is a geometric series. So this term here, everything in here has a magnitude less than 1. So magnitude of x less than 1. So that, I can't quite see that. There we go. So what that means is this geometric series will converge. So write this out. Geometric series. So you remember from, was it algebra or calculus, way back when you learned that the summation from n equals 0 to infinity of x to the n is equal to 1 divided by 1 minus x, provided that the magnitude of x was less than 1. If it ever approached 1 or became greater than 1, then it becomes a divergent series. So we're now going to plug that into this expression here. So let's see, what do we get? So what you get now is you get a gamma is equal to gamma 1 plus, so I'm just going to, all of this stuff here is still untouched. It's just this summation that's going to change. So T12, T21 times gamma 3 e to the minus 2j theta. And then now this thing here goes into my solution over here. So just take this and treat it as x and lump it in, and you get the following. 1 divided by 1 minus gamma 2, gamma 3, e to the minus 2j theta. Okay, so that's all well and good. And this is true for any arbitrary mismatch between the transmission lines and the load. So we're going to make a quick little simplification as well before we do an approximation. So remember that gamma 2 is equal to negative gamma 1 by the symmetry. We also know that T12 is, 1 plus gamma 1, right? And then we're basically plugging in these expressions over here that we wrote down. We do a little bit of substitution, right? So you start plugging in those terms, and you eventually get gamma is equal to gamma 1 plus, so this guy here becomes 1 minus gamma 1, 1 plus gamma 1, gamma 3, e to the minus 2j theta, and then divided by, so that is going to simplify, so I get a 1 over 1, so that gamma 2 is negative gamma 1 here, so that becomes a 1 plus gamma 1, gamma 3, e to the minus 2j theta. Okay, so where are we going with this, and why is this interesting? So you notice we've broken everything down into basically 3 contributions. You have the initial reflection here, this partial reflection. There's the reflection off the load over here, and we've taken away everything in terms of this gamma 2. So that term has disappeared. So the only parameters that really matter is this reflection, and this distance. And now we're going to do, let's see, we're going to make another quickie little change. This guy here, this becomes 1 minus gamma 1 squared here, okay? And then what we can also do is a common denominator with this gamma 1 over here. So what you'll get is something like the following. You have a gamma 1 divided by, what do we get here? 1 plus gamma 1, gamma 3 e to the minus 2j theta times 1 plus gamma 1, gamma 3 e to the minus 2j theta. Okay, so a little common denominator. So that's this term here that we're fixing. And then I will get, and I might as well just extend this out because now I have a common denominator for everything. So I get plus 1 minus gamma 1 squared times gamma 3 e to the minus 2j theta. So I promise we're going somewhere with this. It'll simplify. In particular, let's see. So I'm going to ignore the denominator here real quick. So you'll get a gamma 1 plus gamma 1 squared gamma 3 e to the minus 2j theta plus gamma 3 e to the minus 2j theta minus gamma 1 squared gamma 3 e to the minus 2j theta, and of course divided by that denominator. But the key is these terms are going to gobble each other up. So we now, finally, I'm going to have a gamma 1 plus gamma 3 e to the minus 2j theta divided by 1 plus gamma 1 gamma 3 e to the minus 2j theta. Okay, so that's interesting. Remember, this is an exact equation that will exactly predict the reflection over here. So why is this now interesting? So this is where the notion of small reflections comes into play. Let's suppose, hypothetically, this mismatch here between my transmission line and this transmission line, my 1 and my 2, is very small. And also that the mismatch between this line and this load is also somewhat small. Okay, so the thinking along these lines is you might have a series of transmission lines. It could look something like this, with a whole bunch of lines, all gradually, say, approaching some load here. So that's kind of the motivation for something like this. What happens if I want to do something like this, where this is n lines, and this could be like 50 ohm impedance here, then it becomes like 55, 65, 75, 85, 100, right? So each little mismatch here is relatively small. If I have a bunch of them, I have a whole bunch of little reflections getting up to, sort of adding up to a large reflection. So that's kind of the motivation you can imagine for this, theory of small reflections going on here. If I have a whole bunch of these sections, then this little approximation is going to now make sense. So the theory of small reflections is just going to say that these mismatches are relatively tiny, which implies your gamma n's are relatively close to 0. The nth mismatch here between any of these terms is fairly small. It doesn't have to be like super duper small, it just has to be kind of small-ish. And the reason why we can get away with that is, remember, this product here, if I have two small numbers and I multiply them together, I get a very small number here. So if I assume my reflections are relatively small, like say something like 0.1, then this product here will be something like 0.01 because they multiply together. So what you get is basically gamma 1, gamma 3. That little factor here is negligible. Okay. So it's not appropriate to really say less than 0. We'll say gamma n is very much less than 1, but it's not approximately 0. They're just small numbers. But if I have small numbers multiplied together, I get very, very small numbers that are approximately 0. So the upshot of that is this term approximately goes away if I have relatively small mismatches between these lines. So what you finally are left with, let's just move it way over here. We'll get gamma, my net reflection coefficient is approximately, not equals, just approximately, gamma 1 plus gamma 3 times e to the minus 2j theta. Okay, so that is the interesting result here. If I just have relatively minor mismatches, I can approximate all of that as a very simple little expression like this guy here. And by the way, if you look at the book, they mess up this step here. They actually said, by mistake, they gave it a 1. That is not correct. When these values are small and they multiply together, they're supposed to go to 0. So make a note in your textbook that that is a typo. Okay, then the approximation works and you can get to this result. Okay, so that is the theory of small reflections. And it's going to allow us to do some interesting mathematical trickery when we start getting n-length sections here. of different electrical sizes, okay? So there you go. This is our result here that we care about. And all we had to do is make one little approximation, which is not entirely unreasonable to get here.